Okay, so the next part is stack smashing. And we've talked about what happens when you don't size the buffers properly in your program. This is how you weaponize that into code execution. Okay, so how many of you have heard of stack smashing? It's one of these old school vulnerabilities. You don't see this anymore, really, because the countermeasures are so good. But it used to be highly prevalent. So in 2004, 75% of the exploits were using this method. And there's lots of examples of worms, self-propagating malware throughout history. So it's not common, but it's really a useful example to teach computer architecture and computer systems from, which is why we're covering it. You have to intentionally tell the compiler to not put protections in order to have the levels that I've given you. So there's that. So what we're going to talk about is how it works. And
they didn't have those protections. That's all after Mac in.
Yeah, they didn't have it before. So this is circa 2000. So in fact, this was the peak because in circa 2004, we started really putting in compiler protections, operating system protections, all sorts of things. And we'll get to the countermeasures at the end of this.
2004 would have been when Windows XP Service Pack 2 was released.
Yeah, except Windows didn't really get anything until Windows Vista. So Windows Vista was the first operating system that took buffer overflows seriously.
That's not sad.
Yeah.
Because Vista was so good.
Yeah. So, since we just covered function calls, this is the opportune time for you to learn this. So you all know what happens when you have main, and main calls this function, and function has a variable here, x. You have something that looks like this in terms of the stack layout. So again, your stack has higher memory addresses on top, lower addresses on bottom. This is the bottom of your stack, and the stack grows from high to low. So here is the stack frame for main. And then when main calls function, this is the return address that gets pushed on. And then if you're managing frames, there's a frame pointer. And then there's an allocation for a local variable x that you have in this function. So this is function stack frame, this is main stack frame, and this is the layout, just to refresh your memory from last class. So here's another function. You have this variable x. You have a buffer that's 8 characters long. You do a mem copy into this buffer. You say, I want these bytes, A, B, C, D, E, F, G, and I only want you to copy 8 bytes. So this will actually copy 7 characters plus a null into that buffer. And then you're going to do a printf. I'm going to printf the string, which is buffer, the pointer to the buffer, and then the decimal x, which is this long decimal. Now this should give you what output? A, B, C, D, E, F, G, and then null, 0.
Yeah.
So this is what it looks like on the stack, right? So you have the return address, the frame pointer, the variable x, and then this buffer stored right after it, 8 bytes. So when you send in A, B, C, D, E, F, G, it starts from the low address, right? So here are the low addresses on the going down, and then it does from the least significant byte all the way to the most significant byte, A, B, C, D, E, F, G, null. And you stopped exactly where this buffer ends, so that's good. And then 0 is 0. You're fine. It didn't touch that. Okay. So what happens with this? So now I have a character buffer of 8, same thing, but instead my mem copy is A, B, C, D all the way to K, length 12, and I do this mem copy. What's my stack going to look like?
It's going to overwrite the long.
It's going to overwrite the long. So instead, you get A, B, C, D, E, F, G, H. This is ASCII for I, ASCII for J, ASCII for K, right? And then when you do that print, it's going to say, well, what is that in decimal? It's 7,039,593. So it's a memory corruption bug. When you don't properly balance check this mem copy, or if you don't properly use the string, like a length delimited string copy, you get this issue also. Okay. Yeah.
good to like take the long S and find like the perfect number, so that when you truncate the right number of characters, it'll call something else.
We'll get to this. We'll get to how you weaponize this. Did you have a question?
No, that was.
Okay, you're projecting. You're skipping ahead. All right. Well, I'll give you. So basically, the buffer overflow attack is to trick the program into overwriting memory it shouldn't. So, right, you have this buffer, and you can destroy everything above you. Basically, all your callers frame, and the caller's frame. All the important stuff above you, you can destroy. Okay. So what can we do when we mess up the program's memory? What might we want to do? Look at the stack. Okay. Yeah, which address? The return address. Yeah, how do you hijack execution? Well, eventually this function's going to return, and it's going to return to this return address. And who controls that return address now? We do, yeah. We. All of you.
Doesn't this have the issue where you have to know how many variables are inside the function that you're overriding?
You do, yes. That's what a debugger is for.
That's true. That's true. Never mind. I guess it tells you.
Or you could brute force it. We'll talk about if you're doing it in the dark, there are ways to try and
is it just like kind of trial and error?
Trial and error, spamming is a good one. We'll get to the art of it, basically. Yeah, you could see, so when you really mess up the return address, you'll get a segmentation fault. So you can exactly target, in fact, this is what I would recommend on your homework. You probe it with strings, like all A's, and then until you get a seg fault, and then you're like, okay, that's where I'm starting to mess up with the return address. Because then it's corrupting the return address and going somewhere else. You could do it that way, or in the debugger, you can give it a well-formed string of characters, and then when it returns, it tries to return to an address, and those will be like ASCII characters that you'll be like, oh, that's M, and N. That's that part of the string.
Okay.
So these are techniques. I think in those levels, I recommend these strategies for you to use. So use them. Well, hopefully not, but we'll see. So that is the heart of the buffer overflow attack. Overflow the vulnerable buffer, figure out a way to write your return address in here, and then at the end of that function, eventually this will get returned to, and then you'll have hijacked execution. Okay. All right. To add on top of this, eventually you want your code to run. So we talked about simply corrupting execution, but you actually want to inject something too. And so what you can do is in this vulnerable buffer, you could inject malicious code and then figure out a way to return to it, and then you would get your own code to run. So that's the real trick.
That's what I was thinking, because you can only do this with virtual address. Like, you have to inject your code into that program virtual memory space.
And this is how you do it. So you need some way of injecting code, and then this would be a way. Because the buffer is vulnerable already, that's what you put your code in, and then you would just try and get this return address to return into it, and then boom, you've hijacked that entire process. Okay. So here's another picture. Stack is growing from high on the right to low on the left. You overflow with injected data. You want to hit this. You want to inject your malicious code, get a new address, get the new address which points to the beginning of this buffer, and have it returned to it.
Isn't it technically not the buffer? It's the local variable that you have that the buffer is going into, right?
Yeah, the buffer is the local variable in this case. So all buffers, when you declare it in a function, those are local variables.
Yeah.
They're stored on the stack.
Well, I was just thinking like the difference between like the buffer for like the different places where you can store.
That isn't typically part of, well, that can get mapped into your address space, but those are,
Yeah, typically outside. That's why I wrote.
Yeah. Okay, so that's ideally what you want, and this is what we're going to sort of scaffold our way up to. So the first problem, where is the return address located? This is your question. You don't really know how much stuff is in between your startup address, your startup buffer, and that return address. So how do you get around that? Well, one of the things is you could probe it like I just mentioned. Or what you could do is you could take this new address, if you knew what this address was, and you could spam it all over. Yeah, every word beyond this buffer, you spam with the new return address. One of them will hit, right? Assuming you're properly aligned, then you can guarantee that it will return to your address. Okay. All right. Well, problem number 2, you don't know where the malicious code starts. What address am I going to stick in there, right? Because I have to actually find the beginning of this buffer, the virtual memory address of this buffer, in order for me to return into it. Okay. And these addresses are absolute and not relative. Although in 64-bit addressing, they are relative to the instruction pointer, but they used to not be relative. But still, if we solve this problem, this is trivial. Okay. So how do you find the insertion address? You have to know where the beginning of this buffer is. You remember that code snippet that I did a call followed by a pop? You could use something like that to try and figure out the memory layout of a binary. The other thing you can do is use a debugger, right? We can GDB, set a breakpoint at main, figure out like the parameters. We could like set a breakpoint at strcpy, and then we could just figure out what is in RDI. RDI points to the buffer, and you'd be like, okay, and typically for like open source distributions and like even Windows, you have a copy of Windows, I'll just try and launch it in a debugger and figure out what that address is. So here is an example, just in GDB, set a breakpoint at main, print what the stack pointer, or print what the buffer is, and you say, okay, there's the address of that buffer somewhere in memory. Okay, what happens if you miss? So here is some malicious code, and I'll get to what this malicious code is. What happens if you're not quite exact in your buffer, and you jump either above it or in the middle? It's garbage. So what can I do to make this always run? What can I do to increase my chances, just in case I just missed by a couple bytes here or there?
Use the function pointer set stuff. So if you can, what you do is you dynamically link it to make it so that way you just write to whatever thing is the global GOT table, right? You can do something like that.
I imagine you could. I don't know if I've...
Could you pad your code with a bunch of knobs?
You could pad your code with a bunch of knobs, right? So you guys know the no-op instruction. It's hex 90. You could put it in your buffer. From the beginning of the buffer, you could put 100 nops, and then you can be 100 bytes off in your return address, and it will hit this nop sled, and then eventually hit your malicious code, right? So in fact, it could be a nop, it could be a test quad EAX with itself, and then just all the way down.
That's cheating.
Can you pad the bottom of the code with jumps that jump like a relative value up?
You could do that as well. And so if you're using relative addressing and, your relative jump has to be somewhere in the nop sled. Yeah. And this is just because what's
You
up?
don't really care about being that accurate. You have 100 nops, so just aim for somewhere around 50.
Basically, yeah. And so one of the countermeasures to this is to randomize addresses, right? This relies on you knowing what address to return to. And so that's okay, but if this buffer is big enough, then you've got a huge space to guess, right? And like if I put if I have a 1 megabyte buffer and I'm able to put 1 megabyte of nops in there, well then I can just run that thing over and over again until I get a randomization that hits me. And you guys know the birthday paradox?
Yes.
It's that kind of thing where, the chances of you having a shared birthday, especially in this room, it's just because of the law of probabilities, is pretty high. I think it's 23 people, and then
be about 97%.
Yeah, something like that. That's what happens. So even if you do have this thing which is randomizing every single invocation, the buffer's big enough. All you have to do is keep on repeating the execution, the exploit, and you repeat it. It's a computer, 100,000 times, and eventually you only care about the one time that it works. So again, this is something.
The larger your insertion is, then the less random it's going to be.
The less number of times you have to execute. So yeah.
Well, this is all talking about static, like static attacks, right? This is something you spend some time, you figure out this attack, and then that attack is the way that you do it for this thing, right? Like for this one exploit and this one code.
Sure.
Program.
That's the way exploits are. Yep.
Yeah,
You would fix, and because we have homogeneity in the software that we run, you would just pick the code base that's probably the most vulnerable, and you look for an exploit like this.
So if you want to go attack Windows, you look at the kernel. Not like your browser.
Actually, Windows is pretty darn secure now. Yeah, they spent like the last 3 or 4 years really locking that sucker down. Yeah. Well, Windows.
Oh yeah.
Yeah. So yeah, you don't see a lot.
What's their bounty right now?
You can tell how secure something is by how high the bug bounty is. And so the higher that price is, then you're like, okay, those guys are putting their money where their mouth is. So I don't know what the bug bounty is on Windows. Okay.
Windows is about $5.
All right, so this is the anatomy of a buffer overflow attack. Okay, so we have a means for executing our own code. What code should we execute? What is that malicious payload? And so this is the last piece of it. What code do you want to run on that target machine? So how do you all typically access a machine remotely by? What do? You SSH into it, and on the other side, you are given a command line, a shell, right? So it would be nice if you could execute code that gives you a shell, right? You send a web request to a web server, and it returns an interactive shell.
Sounds good.
Yes.
I can do that.
Yeah, that's basically what the exploit is.
Password,
Yeah. Okay. But is a shell enough? If you had a shell, could you tamper with that machine's Etsy password? No. You want more than just shell access. You want a root shell. You want code that gets you to the highest privilege level. So you want two things here. So you want what's on Linux is a setuid root program that has a buffer overflow. And you want that thing to get you this UID of 0 and then force it to execute bin shell. Then you've got a root shell on that system, and then it's game over for that machine. Okay.
Where are system variables stored? Inside is that all kernel level, or do you have any access to it when you're inside the assembly?
Depends on which pages it's stored on. Obviously, some kernel variables are in the high gigabyte of memory, which you can only get access to via the system call interface. So you don't have direct access to those. But other variables, like the C runtime support in your binary, that's up in the stack region. Your environment variables are there, so it depends. Depends what you mean by system variables.
Oh, because that tells you what your UID is. Stuff like that.
You can get that. So your UID is typically an environment variable, and that is part of the stack. So above main's stack frame, so we have main, and then we have your code, your functions. Above that are your environment variables, and your arguments. Actually, the arguments to the program are actually stored up there too. So yeah. Okay, so how do you spawn a root shell? Well, in C, the C library way of doing this are these two calls. You do a setuid to 0, and then an exec VE of bin shell with certain arguments and certain environment variables. So this is sort of your interface to the operating system. So if you wrote this as a C program and executed it, it would give you a shell. It wouldn't necessarily give you root privileges, because an administrator has to set the UID bit on this binary that you've compiled in order for it to actually get this to be a setuid program. Okay, so this, when you compile this is just assembly, just like everything else, right? So if I compile this and get the assembly code for it, I can just use that as my code to inject, and then if I can get a return to execute that, then I have a setuid root shell. Okay. So for simplicity, typically if you are injecting shell, this is called shell code. So there's, if you go to shellstorm.com, there's like thousands of different shell codes for all the different architectures that are out there, and they're all doing pretty much this, similar to this. For simplicity, instead of doing an exec VE of this, instead of constructing all of this, you would simply point this to null, point that to null, create a string, and get the pointer, the first argument, to point to the string, and then you're done. Okay. So let's see. Okay. So there's some issues that we need to take care of. So we compile the setuid and the exec VE into assembly. But one of the things that we have to be aware of is that any of the nulls in the assembly, if you're gonna blow up a vulnerable stir copy, if you have any nulls in the malicious code that you're injecting into this buffer, it will immediately terminate the stir copy. So you have to make sure your malicious code doesn't have any nulls in it. So that's one issue. The other issue is that you have to be able to access your data deterministically. So we don't have a data section. We can't inject code that has a .data section in it that a linker is going to resolve for us. We're actually injecting code into a live running process. There is no linker there, but we're trying to figure out how to point our assembly code to bin shell, a data string. So we have to figure out this in assembly. And so in order to do so, I'm going to walk you through, this is shell code. And this is what we're going to try and get into that buffer and execute it. And I'm going to walk you through this. The first thing you'll note are the two syscalls. And so this is the syscall setuid and the syscall execve. And if you go into the Linux sort of the system call interface header, you can see that hex 69 is the system call number for setuid, and hex 3b is the system call number for execve. And just like the parameters for your function calls, system calls have a calling convention. And the calling convention for system calls, one of them is to put the system call number you want to invoke in RAX, or in the low byte of RAX. And so that's why you see that this is here. And then, much like your function calls, your parameter, your first parameter is stored in RDI. Okay? So this is slightly different than your function call interface in that this is actually going to invoke the kernel. This is your entry point into the kernel, and this flips the supervisor bit and allows you to jump into the kernel code. So you're running in a privileged state. It's the same process instance, but it's running in an elevated state, running kernel code. So this is set my first parameter to 0, move 69 into the RAX, and then call syscall. So that's setuid 0. That's the easier one. The harder one is execve of, and I'm missing the double quotes here, of bin shell. So this is the setuid 0. I'm going to have to explain this in pieces. The first thing is you want to create this bin shell string onto the stack. Because the only thing that you have is you're injecting into the stack. And so you can use push quads to push a string onto the stack. But here's the thing about pushing a string onto the stack. All strings end with null. So you can't really push a string onto the stack because it's got a null in it. So in this case, this is, and you can do the ASCII for this. this is slash bin, or this is slash, the 2F is slash, and then this is bin/sh, if you can parse hex. But it's got this extra FF in it. Why is that there? Well, it's because that's going to be turned into a null. So if you see this, you zero out RDX, you put this string into RBX, and then you shift right by 8 bits. All right. Where's the null? The null is over here at the end of SH, right? And then this gets pushed off. So this, yeah, you're right. This is padding. So this just gets pushed off the end, and this allows this string to be bin shell. And then what you can do is you can move that register on the stack, and then you're going to take the RDI, you're going to move the stack pointer to RDI, and now this is the pointer. RDI is now a pointer to your string bin shell. So that's your assembly code. So you create bin shell null, push it onto the stack, and then this gets RDI to point to it, because your stack pointer now is pointing to that string. And then you zero out RAX, and this is going to be for the other two parameters. You're going to push several nulls onto the stack, and then get the RSI argument to point to it, because you have, in exec VE, you have your two other parameters. This is just making sure the nulls get there, and then you can do an exec VE. So given what you know about assembly, you should be able to see that, yeah, this does those two system calls.
Could you XOR instead of bit shifting to get 0 on you?
Yes, you could. XOR with what, though?
Because then you'd have to have. Yeah, you'd have to have like 0.
I think this is the most elegant.
Probably.
Yeah, because it's just one shift.
You get what?
If you could use XOR. I don't think XORing so he's asking, just start your string with 2F and then put like bogus data on this end and then XOR it away.
Right. The thing is, I think that you'd have to have like zeros in the value that you're XORing. If you're trying to do it.
Well, if this were FF and you XORed it with the FF, that 1 byte, then you'd be okay. That would turn into 0. But yeah, that's harder for me to think about. This I actually can sort of wrap my head around that. I can't wrap. Yeah, it's harder to wrap my head around the other way.
I think about XOR as a possible like a function that can store some other information inside of another variable. So you can XOR something and store the information in there, and that's sort of get retrieve that information.
Yeah, in
so
this.
If you embed information in something and XOR that, and you can then remove it. Kind of like having glasses with one shade of red, one shade of blue, then you can use that to read like a hidden message. Yeah.
So the thing is, you have to make sure that when you encode it, you don't get nulls. Like so, in order to get the XOR to work, you have to make sure it doesn't rely on there being nulls in the input to generate. So I think this works.
Could you use stuff like XOR to create zeros in your
Yes, in fact, that's what this is, right? I don't want a move quad $0 into RDI. I want an XOR quad RDI to itself. That creates my null without putting a null in the instruction. Because again, this is all being injected. And if you look, when you assemble this, so if you do this, put it in main, and we're going to talk about this next class, embedding assembly directly in your main function is basically what this does. This is equivalent to this. So when you compile this, or assemble this, not compile it, assemble it, these are the bytes you get. What you could do is just declare this as an array, and then cast it into a function pointer. You don't have to understand that. This is basically like, yeah, cast that to a function pointer, and then call it is the bottom. And then this would get the exact same effect. Invoke bin shell. So this is actually in there. You could just copy and paste it in your program and get a bin shell. The set UID won't work, obviously, because unless you have root privileges on your machine. But you'd at least get a shell.
So if you could inject this into real code,
then you would get a root shell. Yes.
I do understand the casting now.
So you're
You
saying,
do. Good. Because I don't.
So you're saying if I SSH now in ATA and I try this,
Well, you have to find a vulnerable...
just, let's say, like even the local server.
Well, you have to try really hard to find a vulnerable binary, and you have to deal with the fact that everything is randomized now.
Okay. Just for playing with
And
it.
you have to deal with the fact that so they finally got around to putting stack protections, so there's no execute bits. So there's page permissions that basically say don't execute anything on the stack. That page, you can, so in fact, here's the rule of thumb. If you have a page that's writable, it cannot be executable. And if you have a page that's executable, it has to be read-only. Those are the things that every single page in your process's address space should adhere to that. So no injecting code into the heap, because that's writable. No injecting code into the stack, that's writable. So that rule works pretty well in terms of eliminating code execution attacks. Yes.
And also, Linus Torvalds quite recently got into like a immense spaz that he tends to do about someone who is complaining about the fact that when they like hack on the kernel and mess around, that they like to turn off the address randomization and then just use like pure hex values out of the addresses for like looking up things and making sure everything's working and all that stuff. They like to do that on hacking the code, and Linus told them that they were stupid idiots because for the first part, that's even when you turn off the randomization, it's not that reliable anymore. So like you'll chase down a bunch of rabbit holes before you find out what you're actually looking for. And then secondly, he's like, because of idiots like you, I'm considering just completely disabling the ability to even turn off randomization. There's no reason you should never not randomize.
It's not impossible to turn. Like he can't.
So if you can replace the kernel on a machine with one that already has the randomization disabled, and then hot load that in the bootloader, then you have non-randomized addresses, but you still have all the modern like locking and stuff.
All right. So that is basically your. Now we have all the pieces, right? We have the thing we want to. We have an obsolete. We have the thing we want to inject. We can get the address, and then we can return to that. In your homework, I don't want you to do this part. So what I want you to do is there's a vulnerable buffer, and I want you to get the return address to return to print good. That's how you solve that level. And one of the nice things that I've done for you is that print good happens to be located in an ASCII range. So the characters are letters, are printable letters. So you'll overflow that buffer with whatever characters you want, and then where you're overwriting the return address, just the characters that represent those the ASCII addresses is all you need. All right.
So this was pretty much sum up. So for this, you overflow the buffer until you get to change the return address. So the instruction point, when it hits that, it jumps to a new spot, which will be also the stack, or this.
No. So you're injecting, and the new address is not going to be onto the stack anymore.
Okay.
In your level. So I don't want you to do the knobsled in the shell code because that would just then you would have to write shell code that would output print good to standard out, which can be done. You can actually write code that calls the system call write on standard out to print good job. You could solve it that way if you wanted to. What I am asking you for instead is to
It's much easier.
just overwrite this to the print good that's actually existing in the binary, but it's uncallable. Right now, there's no way of invoking it from main, but because you have hijacked the stack frame, you can call whatever function is in that binary that you want. Yeah. Okay.
This is part of the new homework
The new binaries that I unlocked today, and they're labeled under 310, unfortunately, but those are all the 310 binaries are now solvable, given what I've talked about today. Okay. So that mem copy and stir copy, they're not the only ones that have these buffer overflow issues. The gets call has this issue where it's not length delimited how many characters to get. The so strcpy, strcat, scanfs, fscanfs, and string scanfs, they're all vulnerable if all you're using is %s. If you're not length delimiting the format string, you have this issue. Okay. So I am going to help you visualize this now. And in fact, there's a couple of internet resources that allow you to, in real time, enter in a buffer and see it blow up the stack. And I think this, like, if you go through these examples and the URLs that I point you to, you should be able to get these levels pretty easily. Okay, so here is an example. I have call echo, and it's calling echo. And within echo, I have this vulnerable buffer. It's a 4-byte buffer that I do a gets on. And of course, this can get blown up. This can blow up echo. So if you do something like this, buff demo, and you type a string and it goes all the way out to this, you can get this to return. So this did not hit the return address. But if you add one more character, you get a seg fault. So this is the strategy I mentioned earlier. You could just probe it with strings that slowly increase. And then as soon as you get to the character that causes you a segmentation fault, then you probably corrupted the return address to point to some random location that hasn't been allocated.
It also tells you how big your buffer is, if it's even or odd, stuff like that, right?
Yeah. And then, moreover, if this is in a debugger, you can actually see the ASCII characters as they're filling up your stack. And you can sort of see when you get this segmentation fault, it'll give you the address that caused that segmentation fault. And so this is where if you have if you planned your pattern of characters right, you can uniquely identify the characters here that map into the return address that you want to overflow. So that would be a trick that I would suggest that you use. Okay. So here is a picture of it. When you compile echo and call echo, so here's call echo, and this is as you would think. It would move, just call quad echo, and then within echo, you allocate space for local variables, and then you move the stack pointer into RDI, and because the stack pointer is now pointing to your local variables, this is pointing to buff. After you do the subtraction, the stack pointer points to your buffer. You put that in RDI and call gets, and then okay. So the return address on this call quad is 406F6. This instruction allocates local variables, and so this is what your stack looks like. So in the call echo, your return address is pushed onto the stack, and then you are inside of echo. So here's your return address. You're inside echo. You call this buffer. Or you do a gets on this buffer. The buffer, the local frame in echo, you make room for the local variables. And so hex 18 is 24 bytes. So 20 bytes are unused, and then you have your 4 bytes of buff. That's what this allocation does. And so when you're doing your gets, you see that when you have this string, 0 through 9, 0 through 9, 0 through 2, this fills up the unused space. And this happens to put the null right there. So it doesn't corrupt that return address. If you go another character, or another 2 characters, you'll get the 3 and the 4 there. This is an address that will lead you to a segmentation fault. And so this is the visual of what's going on when you blow up that buffer and you start going into the return address. Okay. Are there questions about what's going on here? Yeah. Yeah, to be the address of print good. Yeah. And so all of this stuff can be whatever you like, but these have to be the special characters that will make up print good. And you got to remember your endianness, right? You're injecting the least significant byte first. So you have to figure out, oh, well, what's print good's least significant byte? That has to be first. And then the next significant in order to build that address on the stack properly.
If we're going to brute force the address, can't we just have the address for return address in the end and just...
You're not brute forcing the address. You know the address that you want to return to.
Okay, so but we're brute forcing the return address. Like,
oh, you're brute forcing where this is in memory? Yeah. You don't have to. You could actually figure it out through the debugger if you want, if you'd like. In fact, that technique of putting a well-known string in there and then based on where the debugger crashes, which address the debugger is trying to get at when it crashes, and identifying those characters, you could easily, do it directly. Okay. Here are the 2 levels that I'm going to demo for you. You can do this yourself as well, but you need an account on PicoCTF. They're free to create. So I'll show you this using my account. Hang on a second. Before I do that, I need to log in.
Is it Pico like the editor Pico?
Yes, it is. Or as in very tiny. All right. All right. So here is the code that you're running.
Can you use it a little bit later?
Yeah. In fact, let me. Unfortunately, the animation that I want to show you is off here on the right. Rats! Alright. So, let me get the code better. Okay, so your vulnerable buffer is right here. Here's the stir copy. It's taking some input that you gave it. So you're sending in argv, and argv is getting passed right to vuln. And so argv is not bounds checked. So when you do this stir copy from your input into this buffer, this is only a 16-byte buffer. Not only can you blow up the return address, you can blow up this secret. And right now this secret is set to 0. But if you can get the secret to equal code face, then this program will give you a shell. So that's the first level. We'll do both of these levels, but this is the first one. And what they give you is this really cool stack diagram on the right here, which is what I want to show you. Oh wow, they made this mobile friendly, so you could probably do this on your cell phones. Check that out. All right. So this is the input. So this is going to be argv. And what you do is, when you type in your input, you'll see that the stack gets updated. So here is your stack frame. Your buffer's on the bottom, and you have some padding. And then here is the variable secret. And then your return address is somewhere up there. But in this level, all you need to do is corrupt secret. So if I do, say, AA, BB, CC, ED, you see it's this is AA, BB, CC, DD. And then you EE. I don't want an I there. I wanted, this has to equal code face. So the way this interface works is if I do a \x CE, I get CE. And this is \SFA. So now my secret is equal to code face. And so if I run this, this should corrupt that stack in a way that solves this level. So let me run. And then, where's the output? Output somewhere here. Ah. Oh wait, I have to. Oh, there it is. And it'll run it automatically. So this gave me a shell. So yeah, there's a. So you see that this overflow 1 binary is setuid. And so it's impossible for you to read this flag.txt unless you have the setuid bit on the group. So because I can read it, the web shell, it gave me a shell. So, all right. The next one is more like what your program is, or where your binaries are. So overflow 2. This is hijacking program execution. And then in this one, they give you the full stack frame. They give you the instruction pointer you're trying to hijack, the frame pointer, and then this vulnerable buffer down here. And again, you want to call the give shell function directly. So this is the same as the print code. In fact, I derive some of these levels based on picoctf levels and other levels that I've seen in CTFs. So here's the code. Here's your vulnerable buffer. All it has is a stir copy. And so now your return address of vuln, you see in main, there is no call to give shell. There's no way to reach give shell in this code. So your job is to overflow vuln in a way that will return to this function. Now, in order to do this, you have to figure out what the address of this function is. So we're going to use object dump to figure that out. So let's go in our web shell. They gave us the command even. Object dump -d overflow 2 and you grep shell. And then overwrite the return address with give shell. This is brilliant. All right, here we go. So where's my shell? Hey, wait. Okay. All right, so it's this 080484AD. So
Why doesn't that work?
the grep command.
Use egrep.
Oh, egrep, out of habit. I was told one time that egrep was better than grep, and I just believed it. This happened decades ago too. I don't know why. I bet you they're the same now. I don't know. So regular expressions, there's ways of implementing it, so it's super fast. And so if you look in the research, the computing literature, that like people are always talking about better ways of implementing regular expressions. And I was told egrep was faster than grep, but if they're the same.
Egrep takes every single thing and interprets it as interprets the whole pattern as an extended regular expression, and it's just like a normal regular expression.
So it's more. It's got different language. Like you can do different things with the regular expression. All right.
Regular expressions, is kind of black magic.
Okay. Because otherwise, I've been typing a lot of extraneous e's my entire computing career.
Basically, because you never used the extended.
Yeah. All right. What was that address again? It was 84. So that's the address we want to inject, but we want to place that in the EIP buffer. So we need to put some characters here in order for this address to end up over on the saved IP. So I'm going to do AA, BB, CC, GD. M. (080484AD). All right, so this should be a winning input. So where is the?
This is simulating a 32-bit machine, right?
Oh yeah, so yeah.
84 would be twice as long.
Yeah, and so for your 64-bit exploit, you're only going to have to overwrite the parts that you need. Obviously, there's going to be a whole bunch of nulls in the high order bits, so you can just ignore that. Okay, so this is the web shell, so hopefully that'll give me the shell on the bottom after I execute this. So I'll type run. and then it will generate the command that will, yeah, so this is the command, overflow2 with the parameter printf, the exact string that I put in, and it gave me the shell. So now I can do a cat flag.text. Oh, gave me a cruddy shell. Yeah, that's when I know the exploit worked. It gave me a crappy shell. So, okay.
That's a function for hacking system.
Yeah, basically.
Is that runs SUID0, or is that just some other users that use SUID?
It's different users that are being SUID. So typically in these CTF levels, you have each level has its own UID, and then you would set UID to the next level, so that if you manage to solve the level, you get the next thing. So that's basically what this is. Again, your flag. Where's the flag? Flag didn't show up.
Feels good.
Okay, so the flag is only readable by the group, and then the binary. This binary is set UID group, so it allows you, if you execute this, you become the overflow2 group, and then the overflow2 group can read that flag. So.
Oh, that's what that means. Okay.
Yeah, I don't know if you. So this requires some knowledge of Unix, which on permissions. Yeah, I think Cat has a web page that does some of this stuff on Unix. Yeah.
Oh no.
You're good.
So that's a set UID.
Set group ID. Yeah, that's correct. Set group ID. All right. So I think you have everything now. You even have do these levels on your own, and then see if you can do the stack smashing levels in your homework. All right, let's talk about countermeasures. So why does this not exist anymore? Or it's very hard to find an overflow. Well, actually, I should take that back. All of these Internet of Things devices, none of those have any of these protections. So this is why buffer overflows are making a comeback. Because of the Internet of Crap, basically. We've got all these embedded controllers that don't have memory, that don't support memory protection, that don't do randomization, that are being, running C programs because these devices, they don't have the resources to run a Python interpreter or a JavaScript interpreter or a Java VM. They don't have the resources for that. So what you do is you write code in C, compile it, and run it on the Internet of Things. And then, of course, all of the old 90s bugs are resurging. So they're, this is not completely useless, actually. Everything old is new again, eh?
Want to hack a toaster?
Yeah, so toasters, refrigerators. And in fact, like if you go to Black Hat, there's always this, they call it junk hacking, because it's all these old methods applied to all the different places that people are doing the same stuff that we've been doing for decades and not learning their lesson. Yes.
I actually was reading like a blog about this one guy who his internet broke for several hours and he couldn't figure out what was wrong. And apparently his router had gone down, and because of someone bought him a Wi-Fi enabled copy maker, everything in the house just connected to that with those the closest available, open, whatever. So his computer just connected to the copy maker and just started working away like
Nice.
normally. The copy maker never returned anything saying I don't do anything useful. So his web client was just silently crashing.
Interesting. All right, so prevention, better code, which is why all of you now probably will never write one of these in your life. So get used to looking at code like this, and if you see something like this in code, run away from that code. This should not happen. And this shows you the maturity level of the programmer, whether or not they can identify patterns that should not happen anymore. So here is an unbounded gets, an unbounded strcpy, unbounded scanf. And so instead of gets, you can use fgets with a size delimiter, or strlcopy with a size delimiter as well, or scanf with a number delimiter in the size. So there's better code. Practice problem. I think there might be a practice problem in the book for this. Oh, The practice problem is for you to come up with the remediation, but I'll show you the remediation. So different versions that are string bounded, or the length bounded, is basically the solution.
So never use get s or put s unless you
Scanf
can
still
control
doesn't
that
have
input.
Yeah, unless you have validated the input yourself ahead of time. Well, and it's hard to do it on gets, right? You can't. You know, this is
Unless
coming.
You were controlling the string.
Yeah,
So-
you can't. Yeah, so yeah, no, gets is bad, and so if you see this in someone's code base, yeah, it's got issues. Okay, here's the practice problem. List 3 problems with the following code. Let me train your pattern recognition.
Yes.
There is in the bottom.
There's just point out the three calls. All right. Let me get people the ability to write this down because this is this is the only attendance thing I can do. So
Also, there is in the performance convention indentation.
Is that scrap paper?
oh yeah, scrap paper. Yeah.
I noticed last week I didn't get my paper turned in. When I got home, I still had it folded.
I'll take it. You have it.
I don't know if I have it.
I think I have time. 20 minutes. All right. So first of all, vulnerable gets. Second of all is this malloc. You're mallocing the string length of the buffer, but the string length doesn't include the null terminator. So you have this off by 1 error. This is very subtle. It's hard to see how this would get weaponized, but it can, especially because this is on the heap. And as soon as you have heap overruns, the thing that's after this malloc is basically accounting information of the heap. It's like pointers. Yeah. And so as soon as you can corrupt those, yeah, you could point that heap pointer to point to the PLT or the GOT, and then that's your game over. And then the vulnerable stir copy that can overrun. Basically, this will overrun the heap because you malloc this on the heap, and then this buffer, if it gets copied in, will blow up that and corrupt the heap. Okay, another countermeasure is the no execute thing, and this is what I mentioned earlier. You can mark memory segments as non-executable. And so before, the stack was both readable, writable, and executable, which is why you could inject shellcode. When you remove the execute privileges on the stack, you can still overflow it. It's just that you can't return into it. You can't point the instruction pointer into the stack. It'll give you a permission problem. Okay. So the homework would still work, right? On a no execute stack, if you're just messing with a return address to point to code that's in the text section, still works. So I didn't need to disable that part of Linux in order for the binaries to work. Okay, so it wasn't until x86-64 that you finally added this explicit execute permission on these memory pages. And this was circa 2003 or 2002. So this is why a lot of the stack smashing went away after that. Okay. Stack guard. This was something that was developed in Beaverton at OGI. The idea, you guys know the canary in the coal mine? I send a canary in there, and if it doesn't come out, it means that there's toxic gas in that coal mine. So I stick a canary on the stack. It's right after the return address. It's protecting the return address. And I insert it. And on the return, if it got overwritten, then I know buffer overflow happened. So the key here is it's a compiler change. So we talked about the compiler generating code for function entry and function exit. Well, as part of the function entry, you insert the canary. And as part of the function return, you check the canary value. That's basically what you're doing. Yeah.
How can you be sure the canary value is a value that you want? Because they could override it to be whatever value.
Yes. So this is the assembly code. So if you have disassembled any of your levels, you might see this thing, stack check fail at PLT. Have you seen any of this? Because I think I left it in there. This is what's happening. So this is moving the canary value, which is in some different part of memory. And obviously you could probably try and get at it, but you're doing it blindly, right? You're moving it into REX, and then you're moving REX onto the stack. So this is where it resides on the stack. you run your code that's got the vulnerable gets and the vulnerable puts, and then at the end of it, what you're going to do is you're going to move the canary, or the memory location that held the canary, back into REX. You're going to XOR that original canary value with REX. If you jump equal, meaning they're equal, you're like, okay, I'm done. If not, then stack check fail, abort. So this is what you get when you execute. Type a string 0, 1, 2, 3, 4, 5, 6. It returns. You do 7. It corrupts that value on the stack and it aborts. Stack smashing detected.
Like if we know that values can be right above our function pointer, right? Return function pointer. Why wouldn't somebody just say, "Hey, I know that's going to be something that I don't want to overwrite"?
Skip it. Yeah, if you can. In fact, actually, that's one of your levels. So there's a canary bypass level that says, "Hey, there's a canary on the stack. If I know the address of the return address, or if I know where the return address is, if I can write directly over the return address and skip the canary, then that's what you have to do. You have to figure out how to corrupt memory without overrunning the canary. You can't. Yeah. Yeah, and you can't spam the return address everywhere. It doesn't work. So yeah, that's canary bypass, and that one's a relatively easy one. You just have to find the address of the return address and then overwrite that. So I didn't make that too difficult. Okay, this is an animation, which I'm going to skip. So another countermeasure is address space layout randomization. So every time you execute a program, it creates a random memory space. Your stack is in a different location every invocation. And this makes it hard when you do a buffer overflow to guess what to use for a return address. It makes it hard, but not impossible. Again, if you can try things millions of times, or if you have a really large buffer to exploit, you can reduce the probability, or increase the probability of exploitation, basically.
Can't you create fragmentation in the memory layout that way? They're randomly allocated different sections so that you don't end up with enough space?
This is a brand new allocation of memory every time you execute. So every time you execute a program, it creates a virtual memory address space that's completely blank. So that's what you're doing. You're just you're creating you're just trying over and over again on a new version of the process.
Okay, but what I'm saying is that if your stack has to be a sequential memory space, then if you are randomizing the address, but can't you just keep doing that until you don't have a contiguous enough space to create problems with your code execution?
So you have the model of creating a new stack on every invocation in the same memory space. You get a completely new memory space every time you invoke. Yeah. It doesn't remember what the previous invocation was. It's just randomly generating you a new layout. Okay. So this became standard. Randomization became standard. You can randomize anything, basically. The stack, the heap, where your shared libraries are loaded, you can randomize that. And all of this stuff has been around now since Vista and Linux 2.4, which is in the 2003-2004 range. And that's when these things started to go away. Okay. And you can execute this binary over and over again, and you can see how that randomizer works. And so adversaries are looking at, can I reverse engineer the random number generator?
That's what I was wondering.
Yeah, so that if I know...
Because you're estimating where it's going to be.
Basically, yeah. So that's where the cat and mouse game has led people to. Okay. All right. Other things you can do is randomize where your global variables are, randomize stack frames in terms of their layout.
That's most secure, right? If you randomize where your stack frames are inside of your memory.
Yeah. Well, that's randomizing the original location of the stack. This is doing that and randomizing how many frames to allocate or how much space, like in your compiler. Say, I'm going to subtract a random amount. I'm going to take the amount that I actually need and then add some random number to it, and that's what I'll allocate. And that makes targeting much more difficult. The real cool thing is system call randomization. So you know that file that I had before that gave you the system call numbers? I told you had the system call numbers. You can generate a random mapping of your system call numbers, recompile your kernel, and then that shellcode, that shellcode doesn't work. That shellcode works on standard Linux system calls. But if you're doing something like Gentoo and compiling everything from scratch and you've randomized your system call numbers, it'll still work, but no other binaries compiled from on other machines will run on yours. You'll have to, only your code will run on your system. So, but that disables adversaries from injecting shellcode, because unless they know your system call number for execve or setuid,
Does it also stop you from being able to run commercial binary?
yes. Well, this is for like Gentoo, right? You're compiling from scratch all the time, and then you would have your own headers, and then it would know. But yeah. So if you're really paranoid, like, yeah. So yeah. Maybe Donald Trump should be doing this kind of thing on his phone, on his Galaxy. Has he got a Galaxy? He's got an Android. Yeah.
I don't think they ever said exactly what.
Okay. We'll see.
That's probably good.
Okay, this is the last slide. So this is a history lesson of why our society has always gone awry. So we had solved all these problems on a system called Multics. I didn't say we as in the royal we. It's like someone else solved it. We as a society. So these people at Bell Labs were working on this precursor to Unix focused on security. So they already knew these issues were existing. And so they were developing in conjunction the operating system and the processor to build a secure computer from the ground up. So imagine that. This is in the 60s. And part of the features were this, a programming language, PL1, where the maximum string length is always specified. And it's part of every single call. This is similar to what we finally get in stuff like Rust, where as part of the data type, an array data type, it's the length of it is part of the type. So you could do bounds checking. And then automatic string truncation if the limits are reached. So the programming language is helping you get rid of these memory corruption errors. It had hardware-based memory protection. So it was taking them a while to implement the memory protections on this processor. And so there are folks, the founders of Intel, who looked at that and were like, you know what, we'll just build something that doesn't have that. And that became the first 8086, or the precursor to 8086, without memory protection. But they wanted to get to market first. They wanted to, and they did, right? The next thing was the stack. And way back when we were looking at the stack, I told you how the direction of the stack, if they would have just changed the direction, it would have avoided all these problems. Because if you think about it, if the frame, the important return address, is in lower addresses, the stack is growing from low addresses to high, and you overrun a buffer in your current frame, you're going into unused memory, into the ether.
Holy.
Right? The return address is, no, but the return address is sitting there right in harm's way. It's like the deer in the headlights.
So like the advantage of growing in one data structure
Is it
down.
like easier to code? Or?
So here's where computer anthropology would be awesome. I actually don't know the answer to that question. But if someone Googles it,
I think
looks it up, and posts it on D2L, I would appreciate
the
that.
advantage of starting at one end of free memory and growing towards the middle, and the other end of free memory and growing towards the middle is you don't need to allocate.
That's true. Yeah. So when you have a limited number of amount of memory, then you can't afford to have. So you don't know how much to allocate for the heap. You don't know how much to allocate to the stack. If you pointed them at each other from one end to the other and grow them towards each other, that might be that could definitely be it.
But still, you can have the stack on the bottom side and the heap on the top. The heap go down and the stack go up. Right? It's just turning it upside down.
But you'd still run into each other.
Well, yeah, but that's the issue that you have here. It doesn't matter.
Yeah, you would have heap issues, but yeah, that's correct. Yes.
What was the question in regards to?
Swap the stack and the heap. Yeah, that could have worked also.
Oh.
Or Anyway, we could have done things differently. Is the take home point? We could have actually waited for Multics. So I went to this talk in 2004 by Earl Bobert. He is one of the designers of Multics. So 40 years after Multics, they brought him in. Like, Why didn't we listen to you? And he made this really prescient comment about our society wanting crap in a hurry. It explains Starbucks versus like Stumptown. So it's the Starbucks generation of crap in a hurry. And what's really scary is that we've seen this thing in Unix and x86. We're seeing it again in the Internet of Things. Again, as a society, we care about features fast. And it could be crap, but just as long as it functions somewhat, we'll buy it. And so we are continually pushing for features. No startup country in the world is looking at security first. They're like, I don't have a security problem unless I have tons of customers, right? So I have to get tons of customers first, and then security, maybe somewhere down the line. This is where we're repeating everything, and it's like watching a train wreck in slow motion. You know this is going to happen, and it's basically we're going to do the exact same things with the internet. In fact, we actually are. This last year, we have CCTV cameras attacking us. It's like, and that's basically, yeah.
Like the whole idea of having those cameras is to make it so that people are more safe
Yes.
and have all
Yes.
the security. It's just,
Also, the Starbucks thing is interesting because the reason why Starbucks is crap is because Starbucks went from small to large really, really stupidly fast. So they actually started using more coffee beans than everyone else in the world combined. So they started hitting about 30, 40, almost 50 or higher % of the entire world's supply of coffee beans. Just Starbucks. So because of that, the flavor of coffee is changed